Hello everyone, my name is Anna Unkjena and I'll present to you our work, the phase response values application of second order digital frequency dependent components for calculating transfer function coefficients in robotic systems. At Modern Po, the development of information management systems and robotic systems takes place in accordance with the Industry 4.0 concept. In the framework of this direction, there is a need to improve, exciting, and develop new approaches to the components development of such system with the critical of mobility, flexibility, the ability to quick restructure, and adaptability to their operating conditions. Exciting over the Internet of Things technology implies the information exchange not only between people and things, but also between things. On the one hand, things equipped with sensors can exchange data and process information without human engaging. And on the other hand, a human can actively participate in the process. For example, when it comes to smart devices or smart enterprise concepts. However, increasing the automation level in all areas allows you to organize production without the people participation. In this regard, robotic industries are in the first place as a robotic platforms. The personal role in this case is reduced to the control of the technological process and response to emergency situations. This task is especially acute for robotic platforms and critical application systems that must operate in difficult conditions without human access. Then there arises a problem of building the robotic computer system capable for a comprehensive rearrangement of their characteristics by soft and hardware tools, depending on the operating condition to increase the system efficiency is relevant. It should be noted that the signal processing path of such system uses frequency-dependent components, representing a combination of hard and software arranged in a complex architecture and including a variety of linkage. Well known in that the frequency-dependent component responses do uniquely depend on the transfer function coefficients. Let's consider the influence of the second-order tunable digital frequency-dependent components. Because well known is that for ease of tuning, the high-order components are built on the basis of first and second orders frequency-dependent components. Such transfer functions is present in the slide. To some transformation, we get a complex transfer coefficients. And based on these coefficients, we get the amplitude frequency response and phase frequency response. It should be noted that similar equations are used to describe the digital filters and typical second-order links at automatical control systems. We consider the influence of the transfer function coefficient on the frequency response of second-order low-pass digital filters as the most used frequency-dependent components used at computer system and control systems. From phase response equation for the Butterworth filter and with respect to the phase response type, we can conclude that the phase response denominator equal to 0. From this conclusion, we can define coefficients B1. For the Chebyshev filter, this solution is not possible because here the phase response has different phase values at frequencies the cutoff level set by the ripple value in the bandwidth. Studies of phase frequency response have shown that one of its main features is not independence on the cutoff frequency, but that depends on the ripple level. This phenomenon is manifested differently in different filters. After all transformation based on previous equations, the coefficients b1 and b2 for the Chebyshev filter will have the next form. Evidently seen, to calculate these coefficients, it is necessary to know the cutoff frequency, phase frequency values at different ripple level values in the bandwidth. It follows from pictures that the phase values at the cutoff frequency depend only the ripple level in the bandwidth. It should be noted that if the ripple level is constant and the cutoff frequency varies, these values doesn't never change. The approximation of these dependencies had the next form. It is worth noting that the expression works at ripple up to 40. If we consider the Chebyshev filter 1 phase values at the limit value equal to minus p, then the expansion into series allows using it only up to the bandwidth ripple level value equal to 35. Next one, we consider the Chebyshev filter 2. Such solution as to Chebyshev filter 1 is not possible because here the phase frequency response has different phase values at the cutoff frequency level set by the ripple value in the band stop. That's why, after all transformation based on previous equation, we get the coefficients b1 and b2. Also, as readily seen, to calculate this coefficient, it is necessary to know the cutoff frequency phase response values in different ripple level values in the band stop. If the ripple level is constant and the cutoff frequency varies, the values doesn't never change. Also, we get the similar approximation of these dependencies. After this study, we have considered the elliptic filter, and also after all transformation based on previous equations, we got the coefficients b1 and b2. As recently seen, also to calculate these coefficients, it is necessary to know the cutoff frequency phase response values at different bandwidth and bandstop ripple values. To obtain the three-dimensional graph approximation, we go the following way. We fix the ripple level in bandstop with this value for each bandwidth ripple values. We determine the phase values, thus having drawn section for the three-dimensional graph. Such a function will be a quadratic equation. The coefficients value a, b, and c have found for different ripple values. The square arrow in to verify experimentally the exposed theoretical provisions, we used an ultrasonic rangefinder installed on the robotic system for assessing the distance for the obstacle. The rangefinder improved accuracy has been achieved by tuning the radiation frequency and accordingly rearrangement of channel for reflected signal process. In the reflected signal process path, we use a digital referenceable filter. It work shown in this picture. For the conclusion, the obtained approximation of the phase response depends on the ripple level and equations for finding the denominator coefficients of the digital filter transfer functions. contributes to a more rapid use them on robotic system. However, the resulting implementation are not quite simple. Therefore, expanding shall be continuing the search for a more convenient implementation on the microprocessor technology. It should be borne in mind that the ripple values don't change in large ranges. Usually they vary in narrow ranges and rarely. In this case, you can pre-calculate and use some pre-prepared values stored in memory. In the case of a sharp change in working condition, these formulas can be useful for operational calculation in order to maintain the best robotic system function.